Lesson number 8, Magnetic Flux Leakage Testing. Introduction to Magnetic Flux Leakage Testing. Similar to magnetic particle testing, the magnetic flux leakage testing method, abbreviated MFL, involves magnetization of the test object by a permanent magnet or by means of an electrical current to seek out crack and corrosion-type discontinuities. Surface or near-surface discontinuities distort the magnetic flux lines to create a leakage field around the discontinuity. However, instead of using visible or fluorescent ferromagnetic particles to visually identify discontinuities, MFL uses a non-contact sensor, typically a Hall effect probe or induction coil, to pick up magnetic flux leakage from discontinuities as an electronic signal. MFL is most frequently applied to industries that incorporate wire rope, piping, and tubing inspection, as well as storage tank floor inspections. MFL got its start from Elmer Speary's experimentations in the 1930s, in which he bridged U-shaped magnetizers with induction coils to inspect ferromagnetic materials. MFL technology slowly matured throughout the 20th century and was originally categorized by ASNT and other NDT governing bodies as an electromagnetic testing technique. It was considered as an electromagnetic testing technique and not as an MT technique because experts in the field determined that the magnetic field sensor, the eddy current induction coil, is the greater discriminator in classifying the evaluation technique. While understanding how a magnetic field can create magnetic field leakages is important, being familiar with the electromagnetic sensor signal response to the leakage field is a better discriminator to differentiate the types of discontinuities. As MFL continued to evolve in the 21st century, with more sophisticated equipment, increased technician proficiency, and more industry applications with numerous sub-techniques, it was decided that MFL would be better served as its own method. Magnetic fields, magnetism, and flux leakage. The MFL and MT methods share many of the same principles and properties for inspecting ferromagnetic materials. Ferromagnetic materials have a magnetic permeability that is much greater than that of air and are strongly attracted to magnetic fields. Ferromagnetic materials include iron, steel, cobalt, nickel, and 400 series stainless steels. A magnet has the property of attracting ferromagnetic materials. The ability to attract or repel is not uniform over the surface of a magnet, but is concentrated at localized areas called poles, both north and south. A magnetic field exists in and around magnets by means of lines of force that enter and exit at the magnet's pole regions. If a ferromagnetic material is magnetized, its magnetic domains are aligned in one direction and generally exhibit the same characteristics and properties as a magnet. Discontinuities within a magnet or ferromagnetic test object will create their own north and south poles. The magnetic field is distorted and expands at the air gap created by the discontinuity to follow the path of least resistance. Magnetic flux leakage. The distortion and expansion of the magnetic field at a discontinuity is called a flux leakage field. With surface breaking or near-surface discontinuities, the leakage field can become quite distorted. However, as the discontinuity distance increases further below the surface, the surrounding material tends to smooth out the field distortion, resulting in a small field disturbance on the surface of the test object. Detecting the leakage field. Search coils and sensors. In magnetic flux leakage, the two most commonly used sensors for detecting magnetic flux leakage are coils and Hall effect sensors. Other sensors, such as magnetodiodes, magnetic recording tape, and Forrester microprobes, are also used. The coil is the most common magnetic flux leakage sensor because of the large surface areas of inspected ferromagnetic parts. Coils can be arranged with their faces parallel or perpendicular to the inspection surface. Coil diameters are normally small, so coil arrays are used to increase coverage. The individual coils in any array might be connected physically or electronically to minimize noise and isolate discontinuity signals. The signals induced in single coils as they pass through leakage fields depend on movement of the coil or field, distance of the coil face to the inspected surface, coil diameter or length relative to discontinuity length, coil windings, coil orientation to the discontinuity. Variations in any of these factors directly influence the amount of electromotive force induced by a coil by a magnetic field. Hall effect element. The Hall effect element is a solid-state sensor that responds to increasing magnetic field intensity passing through it. Hall effect elements are only approximately 100 micrometers, a few thousandths of an inch thick, and are extremely fragile, so they require some form of support and protection. Equipment configuration. The basic MFL configuration requires a magnetic yoke bridged across a search coil or sensor. As the magnetic yoke travels, being pushed or pulled, typically on wheels, across the test specimen surface, any magnetic flux leakage from a discontinuity is picked up by the sensor as a signal. The signal is transmitted to a computer for software analysis that may range from a simple audible alarm to a sophisticated color-coded image map of the entire structure. As the MFL scanner travels in a grid pattern across a holding tank floor, the sensors differentiate between an area with no flux leakage, meaning no discontinuities, and areas with flux leakage, meaning there are discontinuities. As the sensor picks up the flux leakage variations from the test object surface, a corresponding electronic signal is sent to a computer to document the inspection data, mapping, and analysis. The color-coded mapping of the inspection surface quickly shows areas that have material losses from corrosion. Areas in yellow and red have significant material loss, meaning there's more flux leakage, while green and blue indicates less material loss, meaning less flux leakage. Additional considerations. Consistent and optimal inspection quality requires control of the following variables: a good signal-to-noise ratio, a scanner speed control. Maintaining consistent, not too fast and not too slow speed will provide better signal response and resolution. Vibration dampening. Incorporating dampening mechanisms, such as shock-absorbing systems with big soft plastic rubber wheels, software signaling processing, and so on, into the MFL system will help alleviate surface roughness vibration noise. Signal processing. Amplification of leakage field signals while simultaneously filtering noise created from the inspection scanning mechanism is required for maximizing discontinuity sensitivity. Discontinuity notification and threshold gates. Many MFL systems have one or more of the following signal threshold gate systems to alert when a discontinuity is present. A scanner automatic stop. The MFL scanner stops automatically when a discontinuity of a specific magnitude trips a set alarm gate. After evaluation and marking the surface with a paint pen or chalk, the operator starts the system again. A display and/or audible alarm. Many MFL scanners come equipped with a visual display that will change colors or send an audible alarm to notify if a discontinuity is detected. Computer software analysis. Some systems will not trigger an immediate response, but rather display a complete scan as a digital image with scan analysis color-coded by discontinuity magnitude or quantity of discontinuities in a specific area. And that completes this lesson.